Okay, so let's wait for a couple of more minutes to see if anyone joins. Then we can start. Okay, so it's 5-5. Let's start. So welcome everyone, and this is NOC EE-91 NPTEL tutorial on semiconductor devices and circuits. The instructor is Professor Sanjeev Sambandan from IIT Bengaluru. I am Debashish Nandi from IIT Kanpur. I am a PMRF scholar there. So as you know, we go live every week from 5 to 7. And these are some of the prerequisites for the people who are joining online. So it is expected that you at least have gone through the previous year lectures on the which were posted on the course web page, and also it is expected that you have attempted the assignments posted. So that way you will be able to ask your doubts and get the concepts properly. So recorded lecture sessions are, or these tutorial sessions are posted by the NPTEL team, and it will be available on recorded version on YouTube also. So okay, let's begin. This is week 8. So let us begin. Today we'll be going to discuss about BJTs. Okay, mostly BJTs, and if time permits, we'll discuss about MOS capacitor also. So in this question, it is asked that in a uniformly doped BJT, assume that Ne, Nb, and Nc are the emitter base and collector doping in atoms per centimeter cube respectively. If the emitter injection efficiency of the BJT is close to unity, which one of the following is true? Okay, so let us go step by step. So let us first draw a BJT. So generally this would be your BJT construction. There is actually two PN junctions back to back connected. So there are of two types. One is PNP, another one is NPN, right? There are of two types, PNP and NPN. So we can take any one and do the analysis. So this is generally termed as, let us term it as emitter. This is base and this is collector, or shortly C, B and E. So what happens generally? If PN junction is there, it will form some depletion layer, a depletion region around the junction, if we give it sufficient time to equilibrate. Okay, so similarly there will be another depletion region around this. So generally, why did I draw the depletion width in the emitter side smaller and the base side larger? The reason being that it is generally, you see, if the doping concentration is Ne, your Ne is generally greater than Nb. Your Ne is generally greater than Nb, which is greater than Nc. So as you know, the depletion region will be, you know that depletion region is more on the lightly doped side, right? Lightly doped side. So this is why this convention is followed. Okay. So in P side you will have acceptors and in N side you will have donors. Okay. So these are the two depletion regions you will have. Now let us draw the excess carrier concentration per se. This would be, these are the metallurgical junctions which I am showing in with the dashed line, and these are the edges of the depletion region which I will be showing in the dotted line. Okay, so from the PN junction theory, you know that there will be excess carriers present due to the applied biases. Okay, so let me take, it is x direction. So as of now, as we are asked to compute the emitter injection efficiency, so we'll be mainly focusing on this thing. Okay, this is called, by the way, your EBJ, and this is called your CBJ, or your EBJ is emitter base junction and your CBJ is collector base junction. Okay, so what happens is that, let's say this would be your carrier concentration profile. Okay, let's take it in this way. So what happens is that, let us take it, what will be the minority carrier? Minority carrier in P side will be N. So at this point, let this level be delta N subscript E, and this will be delta P subscript B for C. Okay, so now let me add another page. So now let us draw another diagram. Okay, so let us extend this regions. The way your thing is biased is your emitter base junction is generally, or the EB is generally your forward bias, and your this junction is generally reverse biased. So your VBC, this junction is reversed bias. There are other topologies. The way we take the common terminal, based upon that, the topologies can vary as common emitter, common base, and common collector. I think you have gone through those things in the lectures. So as of now, let us think that there is your this boundaries. So I will draw a certain kind of line diagram which will be very helpful in understanding the concepts. Okay, so first let us think. So this arrow will be determine the whole movements, and let's take this arrow to be the electron movement. Okay, so what happens is that, suppose at this place you are applying some positive voltage to the p side, so we can assume that, so what will happen, it will attract the electrons towards it, or we can assume it to be, it is injecting holes to the excess holes to the p side region. Okay, so let us think that it is injecting holes. Okay, so due to this injection of holes, there will be certain amount of current. So let us call this current to be IE. Okay, so what happens at this boundary, also the holes will move forward because this boundary is forward biased. So a certain amount of holes will move forward. Okay, let's call this IEP, and you see at this place you have a negative potential. This is positive and this is negative. Okay, so what happens is that you can think that some of the holes will be trying to move towards this direction. Okay, and due to that a particular current will flow, and that current we call it as recombination current for the time being. Okay, so this is not a vector, this is just the direction of the current due to holes. Fine, now let us take how the electrons will move. Okay, so as this base terminal, this is your base terminal and this is your emitter terminal. So as your base terminal is negatively connected, so we can assume that it is injecting some electrons. Okay, so it is injecting some electrons in this direction. And also what happens, there is a presence of electric field due to this forward bias. So for that, some of the electrons will try to move in this direction also. Okay. And some of the holes will try to move in this direction. So let us call it IEP. And what will happen at these points? At these points, they will recombine. Okay, some of the electrons will recombine with the holes. So you can see that as electrons is moving in this direction, so your current flow will be in this direction. So let's call it IEN. And as this is your electrons movement, so this we called as IB, or the base current. Okay. And what happens that some of the electron will pass through your collector, and for the time being, let's call it ICP. And at this, it is collecting something will happen at this location also, but we are ignoring it for the time being. Okay, because at this region something similar will happen, but we are ignoring because we are interested in the emitter base junction, because we are trying to find out the emitter injection efficiency. Okay, so this is IC. Fine. So can you tell me, as you have studied, can you tell me that what will be the, how do we define the injection efficiency? So first thing you note that uh, if you write KCL at this node, what will be your KCL? Your IE would be IEP plus IEN. This current and this current, right? From this node. At this node, if you write your KCL, what will happen? Your IEP would be equal to your ICP plus IR. And what about at this node? At this node, your IB is equal to IR plus your IEN. This is coming from this side, this is coming from this side and going out of this node. Okay. Now, can any one of you tell me what do we mean by emitter injection efficiency? Emitter injection efficiency. This is denoted as gamma. So what does it mean? It means how efficiently my current is moving from this point to this point. Okay. So how do we define it? We define it in the following manner. It is IEP over IE. That means your this current over this current. Fine. So now can you tell me that, okay, let me do another step and then ask you. This will be IEP, and from this equation we can write that IE equal to IEP plus IEN. Fine. Now can you tell me what type of current is this? What type of current are this? You can unmute and tell me. What type of currents? How many types of current do you know in a semiconductor that flows? So I have only one person. Parts are three.
And diffusion and drift. This is and drift current.
So there are two types of current, right? Drift and diffusion. So what is the major current mechanism in PN junction under forward bias?
and
Drift. Are you sure?
sorry, no diffusion. Minority carrier diffuses.
Minority carrier diffusion, right?
Yes, sir.
That's why there is a current. So now you concentrate on this plot and look at how this IEP. So what will be your IEP? IEP will be your nothing but JEP times your area. Area, what is area? Area is the junction area of EBJ. That means emitter based junction, right? And so what will be your IEP? It will be JEP times A plus JEN times A. Fine. So A will get cancelled. What is JEP? It is due to diffusion. So it will be Q times dP times this of del PB over del X. This is del PB and this is the X direction. Similarly, so how will this diffuse? These carriers will diffuse in this way. So current will flow in this way. And these electrons will diffuse in this way. So current will flow in this way. Right? So again this will be Q dP times del PB over del X plus your Q times dN del NE over del X. What is del PB and del NX? Is the excess carrier or excess minority carrier concentration at these points, depletion region edges. Okay. So now suppose this is your diffusion profile. Okay. Say this is some del P and it will decay, like it will decay exponentially under the diffusion approximation. So if I draw a slope at this point, so what will be this length? This length is nothing but LP, or the we call it diffusion length, right? This we have discussed in the last lecture also. So what happens? You can approximate this thing to be Q dP times your, what is this? Your del PB over LP. Why do we do this? Suppose you try to reduce this length. Okay, there is a collector base junction present at this place. Suppose you try to move this junction in this way. So what will happen? Your this profile will try to be more sharper and sharper. Okay, so after some time this thing will be almost linear. Okay, so for that reason we will be making this approximation. So then what happens? Your this is QDP delta PB over LP plus QDN delta NE over LN. So let us make some more approximation. Let us take this is to be del P by LP to be almost equal to del N by LN. Okay, so we can take this common and Q gets cancelled. So we will be leaving with delta PB over delta PB plus delta NE. So what is delta PB, by the way? Delta PB is Pn0 times e to the power VBE over VT minus 1. This we know from the PN junction theory. And similarly this is e to the power VBE over VT minus 1, and this will be plus NP0. And what is this? This term and this term. This is your minority carrier concentration at equilibrium in N-type base, and this is your minority hole concentration, minority electron concentration in P-type emitter at equilibrium. This we know, right, from the p-n junction theory. So you can write it also in the same way, to the power VBE over VT minus 1, right? So we can see that these things can be cancelled off. So what we will leave with? Pn0 over Pn0 plus Np0. So what is your Pn0? Pn0 is nothing but your intrinsic carrier concentration by Pp0, and this is Ni square by Pp0 plus Ni square by, this is your Ni square by, this is your Pn0, so it will be Nn0. So similarly it will be Nn0, similarly it will be Pp0. Fine. So now what is the Nn0? Can you tell me what is Nn0? Or the N, this is your Nn0 and it is Pp0. That means at equilibrium, what is the carrier concentration of this P type? This will be nothing but your Ne, or the doping concentration of the emitter, and this will be nothing but your doping concentration of base, right, under 100% ionization approximation. So you can write this as 1 over Nb by 1 over, this Ni square gets cancelled, 1 over Nb plus 1 over Ne. So that is your Ne over Nb plus Ne. So this is what? This is your gamma actually, what we have calculated. So your gamma is computed out to be approximately equal to Ne over Ne plus Nb. Now in the question it is asked that the emitter injection efficiency is to be close to unity. That means these things is close to unity. So from that we can easily say that if Ne is much greater than your Nb, or the doping concentration of the emitter is much greater than the doping concentration of base, then your Nb plus Ne will be almost equal to your Ne. That leads to your gamma is almost equal to 1. So this is the condition which is required to be satisfied. So in the modern transistors, if I have to say, this is around your, this is very highly doped, okay, this is around your 10 raised to 19%, and this will be doped, let's say 10 raised to 17. Okay, so this condition has to be met. So this would be your correct answer. Okay, as the constraint is on emitter base junction efficiency, constraint is on emitter base doping only. So from that you can see that if NE is much greater than NB, then we can definitely say that my emitter base junction efficiency will be almost close to unity. Okay, so this is how to go about this problem. You can remember, but it is good to understand the basics. So now let's move on to the next problem. So it is mentioned that the DC current gain of a BJT is 50. Assessing that the emitter junction efficiency is this and the base transport factor is this. Okay. So at this point, let me tell something more about this. So this is called your emitter junction efficiency, and what is your base transport factor? Can you tell me? Base transport factor is defined by B, that is nothing but your ICP over IEP. That means your this quantity over this quantity. Fine. So this is called base transport factor. So what did we have? We had IE equal to IEP plus IEN, and we had ICP plus IR, or let me do it in this way: IEP is equal to IR plus ICP. So this one, and IB equal to IR plus IEN. IB equal to IR plus IEN. And your IC, for the time being, we assume it to be ICP. Okay. So what happens? Your IC by IE, that is called your current gain alpha. Okay. So this I can write as IC over IEP times IEP over IE. What is this quantity? This quantity is nothing but your ICP over IEP, and this is your IEP over IC, IE, right? So this quantity is nothing but your B, or base transport factor, and this quantity is nothing but your gamma, right? Emitter injection efficiency. So we see that your alpha is equal to gamma times beta. Okay. What is alpha? Alpha is IC by IE. So now it is given that, and also we know that from these equations, you see that IE is equal to your IEP plus IEN. What is your IEP? IEP is your ICP plus IR plus IEN, right? And what is IR plus IEN? This is your ICP plus IB from this relation. So we can also see that IE is equal to IC plus IB, or so as to say, if we tell in a broader sense, the current entering here IE would be equal to this IB plus this IC. Okay. So now here if we use the same argument, that your IE is equal to IC plus IB, and let us divide both sides by IC, then I will have this plus IB over IC. This we know that IC by IB is alpha, so IE by IC will be 1 over alpha is equal to 1 plus and this quantity beta is defined as IC over IB. Okay, this is also called a current gain. We will get to know which current gain is to use in which cases of the bias or the configuration, BJT configuration. Okay, so IC by IB, this will be 1 over beta. So if we simplify it, alpha would be equals to beta over beta plus 1. This is beta plus 1 over beta. So we can write it this way. Alpha, we know that it is gamma into B. So what will be my B? B will be nothing but beta over gamma times beta plus 1. So what is beta given in the question? It is given 50 times 51 into what is your gamma given? 0.9995. Okay. So if you compute it, it will come out to be around 0.98. So your base transport factor is equal to B is equal to 0.98. Okay. So did you get that?
Yes, sir.
Okay. So have you studied the lectures?
No, sir, not seen video, only slide.
Only slides. So this assignment you have attempted on the BJT.
No, sir.
Please do attempt the assignment. Okay. It will clarify
Yes.
your concepts. Okay. So let's move on to the next problem. So it is given that for a BJT, common base current gain is alpha and collector base junction reverse by saturation is this. So okay. So what do we mean by common base? If this is your, let's say, PNP transistor and this is your emitter, or rather let me tell you how to write it properly. Okay. Generally what happens, if this is a transistor, the actual dimension will be something like this. So this would be your emitter, this would be your base, this would be your collector. So let's see, let's say this is your WE dash, let's say this is WB dash, and let's say this is your WC dash. Okay. Generally your WC dash will be much greater than your WE dash greater than your WB dash. So this will be very small. Okay. So the proper way to draw a BJT in current scenario is like that. And also how the doping concentration varies. If I draw the doping concentration, this is along x-axis, and let me just demarcate it. So generally your doping concentration would be something like this. Okay. So it will be something like this, and then it will increase for the, there is a substrate will also be there.
Sir,
Yeah,
sir, WC is much greater than WEY.
WC is much greater than WE because we assume that the W's are to be much. Okay, first thing is that this is not much greater, this is greater, this would be much greater. Okay, so WC has to be much more than the diffusion length. Okay, so that if you see the excess carriers, okay, just let me draw it as you have raised the point. If your excess carriers are to be here, So you want your entire thing to get diffused. Okay. So you want this, let's say this is your diffusion length. Let's say it is PNP transistor. So it is your diffusion length Ln. So you want your WC to be, and WC and WE both to be much greater than your Ln. Here there will also be a electron diffusion. Okay, so that you can transfer more amount of current from the emitter to collector. Okay, so that your all of your excess electrons recombines in the collector itself. So this is the main reason. So as I was talking that, as I was telling that your this is your Ne, this is your Nb, and this is your Nc. Okay, so it will be around your 10 raised to, let's say, 18. It will be around raised to 10 raised to 16. It will be around 10 raised to 14 per cc. This will be the typical doping. Okay, so the correct way to write the PNP transistor is that you make it double plus, you make it N, and you make it P plus. Or let me just do it in this way. Okay, so this way you will not be able to mistake that what is your emitter, what is your collector, and what is your base. So what is the common base configuration? These configurations are generally, suppose you are applying some potentials, right? The idea, yeah,
Sir, collector doping is more than the base doping. Na?
which one?
Collector doping and base doping. Base doping should be lightly, base is lightly doped and collector is moderately doped. Na?
Base is likely to, why do you say that?
If that is more, doping is more than uh, uh, con- uh, recombination will be more. If base is moderately doped, then recombination is more.
Okay, okay. If you say so, okay, I'll just get back to you on this. Okay. I think you are right. Just let me cross check it once. Okay. Okay, let's forget this one and let me cross check it once. Okay. Okay, I'll just cross check and tell you, because I was under the impression that due to the small shorter range of the base, you can accommodate that recombination. That will go into the next step. So anyway, you can assume this configurations in such a way that you say if it is your PNP transistor and this is your emitter base and this is your collector. So you want your this thing to be forward biased, and your this collector base junction you want it to be reverse biased. Okay, so this is, and how do you do the biasing? You can just this type of biasing where your base is at a common potential is called a common base configuration. Okay, here your input terminal is emitter, so your input current is IE and your output current is IC. So what is the current gain? Current gain in common base configuration, we generally talk about alpha. Okay, that is your IC over IE. Fine. And in your common emitter configuration, let's say this is your PNP transistor. So how do you bias it? And you take this terminal as your bias. Okay. So what will happen that you bias it in BCE in such a way that your this junction remains reverse biased. Okay. So what is the input current in this case? Input current is this case is your IB and your output is IC. So your current gain in common emitter configuration is your beta IC over IB. This is a general convention we follow. Okay. So now what happens is that you know your IC in common base is your alpha times IE plus your ICO. This is your, what is this, your reverse bias current that will be flowing between the collector base junction, though it is reverse biased, but there will be certain amount of current flowing. So now if you write in this fashion, this relation will always hold. Okay, IE equal to IC plus IB, and this you write as ICO. Then if you take your IC this side, and it will be 1 over alpha times IB plus 1 over 1 minus alpha times ICO. Fine. So this IC, if you see this from this relation we discussed earlier, then you would find out that this is nothing but your beta. Okay. So it is your beta IB plus this will be your beta plus 1 ICO. We have been given alpha. So your IC would be, this is your 0.98 over 1 minus 0.98 times what is your IB? IB is 20 microampere plus your 1 over 1 minus 0.98 times your 1 microampere. Okay. So your IC will be, this is 49 times 20 and this is your 50. So your IC would be 1030 microampere, or it will be around 1.03 milliampere. Okay. So this will be your right option. So next is that if two BJTs are biased at the same collector current with a area this and area that, assuming that all the other device parameters are identical, the intrinsic carrier concentration, these are given. What is the difference of base emitter voltage? Okay. You see your IC is equal to beta times IB, right? And what is your IB? This is your emitter, this is your base, this is your collector. So this is nothing but a PN junction. Okay. So the current through the PN junction, if I just ignore the IC for the time being, will be of what form? Proportional to exponential VBE over VT minus 1. So we generally write IC as IS times e raised to VBE over VT. This IS is called reverse saturation current. It is just a PN junction formulation, okay? So your IC will be IS times, this is the convention, IS times e raised to VBE over VT. So, and what is your VBE? VBE is the bias applied at the emitter base forward bias, emitter base junction which is forward biased, okay? So what happens is that your IC would be equal to, let's say IS would be what, your JS times area. So area times JS times exponential VBE over VT. Okay. Now they are asking us that two BJTs are having same collector current. So this is A1 JS1 exponential VBE1 over VT, A2 JS2 exponential VBE2 over VT. So JS1 depends on the device internal parameters. It will depend on your diffusion length. It will depend on your diffusion constant. It will depend on the width of the base. Okay. So these all are, it is mentioned that all other device parameters are identical. That means these two terms are identical. Okay. So now what can we write? Your A1 over A2 is equal to exponential VBE2 minus VBE1 over VT. Fine. What is your A1 and A2? A1 is given as 0.1 into 0.1 over 100 into 100. Exponential, let's call it delta VBE over VT. And if I, by sign convention, let me take VB1 is greater. So I can simply write your delta VBE is equal to VT times natural logarithm of, what is this, 10 raised to 4, and this is 10 raised to minus 2. So it will be 10 raised to 6. So it will be 6 times 0.026 times natural log of 10. So if you compute, it will come out to be your 0.359 volt or 359 millivolt. Okay. So if that is okay, so let us move on to the next problem. Again, it is mentioned that an NPN BJT having reverse saturation current, this biased in the forward active region with this, and beta may be this. Okay. So tell me one thing. If I draw my, this is your VCE per se, this is your IC. Okay. So if I draw the characteristics in this fashion, and there will be another region. So, and also it will have this kind of characteristics. Can you tell me what are the regions of operation here? Let me mark the regions, and also tell me what are the what are the conditions on the junction or the bias condition on the junction. This is one region. Let's say this is another region, and your this is this is another region, and this is one region, and this is another region. So can you unmute and tell me what are the regions of operation? So what are these? These are various. This is, let's say, VBE1 or your IB1. This is your for a VBE2 or your IB2. Let's say this is IB3. This is for a particular IB4. Can you unmute and tell me, Patsarthi, what are the region of operations?
The first region is saturation region,
Which one?
dotted uh,
This
from
region is called
0 to,
saturation.
yes, sir.
Okay.
And the negative region,
This is called, this yellow region is called,
active region.
okay, active region. What about this red hatched line?
I don't know about that.
This region is called your cutoff region.
Yes, sir.
This region is called green one, your breakdown region. And this pink one is called
A reverse region,
reverse
reverse
active
active region.
region. This is your forward active, okay?
Yes, sir.
So now can you tell me the bias constant on the junctions? So let us make a table. So your this is EBJ. This is your collector base junction. These are the regions. So for forward active, what is the condition on emitter base junction?
Emitter base will be forward and uh, base collector will be reverse.
This is reverse biased, okay? And what about the saturation? And what about cutoff? Try just make an attempt.
Sir, both should be in forward bias.
Which junction should be in forward biased?
And both
For which?
saturation.
For saturation, both will be in forward biased, okay? And for cutoff,
Both should be in reverse bias.
are you sure?
No, sir, sure not. I think so.
And what about the your this reverse active?
Reverse active should be opposite of active region. Uh, First will be in reverse bias and second will be in forward bias.
Okay, fine. I think that is fine. So can you tell me what are the applications of these regions?
For, first, these are act as digital and this is a analog circuit amplifier.
See, first is in amplifier, right?
Yes, sir.
And second is in switch applications.
Switch application.
Saturation will be your switch on and this is switch off, right?
Yes, sir.
Okay. So if that is clear, in our question it is mentioned that the forward active region where the thing is biased. That means your DC load line, your quiescent point is somewhere here. Okay.
Yes, sir.
So now it is mentioned that your, so by the way, if your thing is this is in biased in forward active region, from the thing you can tell me this IC by IB is your beta, right? That is 100 to 150. And what about your IE? IE is your IC plus IB. We want, they asked us to find out maximum emitter current. Fine. So IE would be, if I take IC common, 1 plus IB over IC. So your IC is 1 plus, this is your 1 over beta, right? So can you tell me why did I take IC common? And I am claiming that if IE to be IE max, then beta has to be minimum. That means I will take beta value to be 100. Can you try to answer this question? See, the reason we are following this is that in the forward active region, right? If my thing is biased in the forward active region, then what is your IC? Your IC is almost constant, right? So this quantity IC is almost constant. So whatever your variance in IE, that will be due to your beta, right? So if IE will be maximum, if your beta will be minimum, fine. So now if your IE max I want to compute, I will write simply IC times 1 plus 1 over 100 because I need to take the minimum beta value. So what is your IC? IC is nothing but your IS times exponential VBE over VT times 1.01. So IS is 10 raised to minus 15, okay, times exponential, what is VBE? 700, this is 25 millivolt times 1.01. If you compute, it will come out to be 1.460 into 10 raised to minus 3 ampere. That will come out to be 1460 into 10 raised to minus 6 ampere or 1460 microampere. Okay. So did you get the main crux of the problem? The main crux lies in the fact that at forward active region, IC is fairly constant. So if beta also varies, my IE will vary. Not that my IC will vary, okay? Because at forward active region, my IC is constant. So that is why we can tell that this, if constant, then if beta changes, then my IE will change, okay? So, and the relation we found out to be, if beta is minimum, then my IE will be maximum. Okay. So let's move on to the next problem. Okay, so it is mentioned that and in the injected excess electron concentration profile in the base region is given. Okay, so can from the figure can you tell me what are the inbuilt approximation? They are starting the excess carrier concentration from the metallurgical junction itself. Okay, but it is not the case, right? We have seen that it starts from the depletion edge. In PN junction analysis also you must have seen that. So first thing is that they are ignoring the depletion region. Okay, now what they are telling that instead of your excess carrier decays like exponentially under diffusion approximation, but they are taking it as a linear, right? The thing we have discussed earlier also. If your base is very lesser, how can you tell that? Suppose you have a e to the power minus x kind of profile. Okay, so if x is much less than 1, then your e to the power minus x, if you Taylor expand it, you can write it in this way in the infinite series form. So if your x is much lesser, so you can approximate it to be 1 minus x, and that is your linear profile. So exponential becomes linear when x is much smaller. Okay, so under the same approximation, it is given by default that the profile is linear. Okay, and they want us to compute, and it is biased in the active region. Active region means by default it is forward active region is linear. It is shown in the figure. The area under the emitter base junction is this. Area is given 0.001 centimeter square. Mobility is given. Base region depletion layer is given. Okay, so what is the current? Current is your area into J, current density. So this current density is due to what? Due to diffusion. D of your delta n over dx. So what is this quantity? This is nothing but the slope of this profile. What is the slope? That is 10 raised to 14 by 0.5 into 10 raised to minus 4. This height over this base, that is the slope, and slope is constant throughout x. So is this area is given as 0.001. This we know 10 raised to minus 19. And for Einstein solution, we know this is nothing but 10 to mu. So this is 0.026. And what is your Vt? What is your mu? Mu is given up to be 800 centimeters square plus 4 second. And this slope we have computed it to be 10 raised to 14 over 0.5 into 10 raised to minus 4 in centimeter. Okay, because we are dealing with all the quantities in centimeter. So if you compute this, you will find the current out to be, so this is your 1.6 times 0.026 times 800 times 2 times your, this is minus 3 minus 22 and 18, 10 raised to minus 4. So this will come out to be your 6.656 milliampere. Okay. So again the same principle, just you need to remember that current is due to the diffusion. Okay. So moving on. Okay. So base width modulation in a BJT results in what? Do you have the idea what is base width modulation?
Yes, sir. Change in capacitance. Base,
Change, change in
base width.
capacitance.
Yes, sir. Base width will be changing.
Okay, but that is not
Depletion with
given.
depletion with will change.
Okay. Okay, let us go step by step. Don't unmute yourself. Let us go step by step. Assist me in this in solving this problem. First, tell me that if this is my emitter, let us write it in outside. This is emitter, this is base, this is collector. This is your P type, this is N type, let's say this is P type. So you will have some junction like this. Okay.
Yes, sir.
So by the way, you were mentioning that, right? Your collector concentration will be if you have a, this is your emitter, this is your base, this is your collector. So this is NE, this is NB, this is NC. Okay. And if I need to draw the concentration profile, so how will it be? I was drawing it like that, right? You mentioned that your base will be uh,
Lido.
lightly doped. That is right. With respect to what? Collector? I don't think so. This is your NB and this is your NC. This is around 10 raised to 19, let's say. This will be 10 raised to 17 and this will be 10 raised to 15. Okay, you
Yes,
please
sir.
check it once from your side.
Yes, sir. Yes, sir. You are right. I think so. Why? Because if it is more, and then whole base will be depleted.
Because what happens,
If
if
it
you
is
have
more
a,
depleted, and then whole base will be depleted. Sir, you are right. I am wrong. I was wrong. I think so.
you got the point, right?
Yes, sir.
But again, for the benefit of the audience, if someone is watching the recorded lecture, so just let me complete it. So what happens actually, you will have excess carriers, right? Let us say this is P and P. So you will have what? You will have a, this is, if this is 10 raised to 17, then it will be around 10 raised to some like this, and it will be like that. And there will also be some. So you see, if this junction you dope it higher, these are the excess carrier concentration. Okay, this is your delta NC, delta PC, delta PE, and here you will have be delta NE. So these holes will try to diffuse this side, this will try to diffuse this side, right? But if you, now this is the one case. In the another case where your NC greater than NB, then I will have something like this. Okay.
Yes, sir.
So the transport of holes in this direction is getting more hindered. You see, due to higher slope at this point.
Yes, sir.
So generally this is not correct. Okay. So you remember this will be the your correct profile. Okay. So you generally mention it is a P plus plus N plus P. Okay.
Yes, sir.
Or you can write it that P plus plus N and this is as P minus. Okay. So this
Yes,
will be
sir.
the profile, and also about this width. If this is your WE dash, this is your WB dash, and this is your WC dash. So what are the things I have told? WC dash is greater than WE dash, is much greater than WB dash. This thing has to be very small. Okay. The reason is that this slope will has to drop very fast. Okay. This slope, the more this slope will be, the more this transport will assist. It will assist the whole transport. So there is a thought experiment actually. I did not think that I would cover it. Okay, there is a thought experiment. You can try to think it in this way. This is extra. Okay, a thought experiment. Let's say what you do is that you assume your this is your emitter base junction, and you assume your collector base junction to be far away. Okay, you assume this junction to be EBJ to be CBJ to be far away from EBJ. Then you try to move it closer to EBJ and try to see what is the effect on this diagram. Okay, this is a very good thought experiment for you. You assume CBJ to be far away, and the bias condition you will take it this as forward biased, and this you think is to be shorted. Okay, CBJ to be far away from EBJ and gradually bring CBJ close to emitter base junction. See the effect on excess carrier concentration. Okay, take three cases. Let me say the diffusion length is, let's say in this case LB. Take three cases. Okay, and this will be your WB. In one case you take WB by LB much greater than 1, WB almost close to LB. In another case WB by LB much less than 1. See the effect on this diagram. Okay, you will get much more insight, and once you are done with this you will not be able to forget how the things are. Okay, so yeah, going back to the this was done, right? Going back to this. So what is base width modulation basically? First thing is, please unmute Patsarthi, we are discussing, right? This is in P side you will have negative concentration, this will have positive, this side you will have positive, and this side you will have a negative thing. Okay. Now let me just call this width as a metallurgical width. This is called WB dash or metal. This is called your metallurgical base width. And what is this called? This is called your WB electrical base width. Okay. So first thing, when we discuss about base width modulation, so base width modulation refers to modulation in electrical base width WB, okay, this quantity. That means apart from the depletion region, okay. So then what happens when we go like this, okay. Now if you see the exact phenomena or exact IV characteristics, output characteristics, okay, where do you use this? Okay, so if you see actual output characteristics, how will it look like? Let me just draw it. So what do we draw first? We draw this line, we draw the breakdown line, and we draw a voltage far away in this region. This I will call VA. We'll discuss what is this. So generally what happens, this I will make it dotted, okay. So generally your IV characteristics look something like this. And then it will drop, okay. So generally your IV, this is your VCE, this is your IC, this is your, let's say, VBE1, VBE2, VBE3, VBE4, and let's say VBE5, okay. So what happens, let us be on one plot, okay. Let us be on one of the plot where we make VBE constant. Let us make this to be constant, or we are looking at one IV characteristic, one IC versus VC characteristics for a particular VBE, okay. So first note that your bias is something like that. This is your VBE, or let me just do the nomenclature at VEB, and this is something like that, VEC, okay. So this is for PNP, okay? And this I am drawing for NPN. You can just invert the signs. These all are the same. So by the way, you note that this voltage is your VBC, okay? So VBC is what? VBC is the reverse bias across this PN junction. If this is a PN junction and this is VBC, you note that VBC is the reverse bias, or I have drawn the diode in wrong direction. Do you see that it is a reverse bias junction?
Yes, sir.
So now you assume that you are increasing VCE, okay? That means you are standing at this point. Now you are moving like this, moving on this direction, okay? That means your VCE, VBE is fixed and you are increasing VCE. So your VCE, or if in that junction, okay, let me just change the nomenclature quickly so it can be on the same thing. This is your mod IC. Let's say this is your VEB5, VEB4, VEB3, VEB2, VEB1, and this is your VEC. Okay, and this is also for your PNP transistor. Let us take it in this way. So your VEC is your VEB minus VCB. Do you agree with this?
Yes, sir.
How are you sure that this is right? Because VE minus VC is your VEC. This is your VE minus VB minus your VC minus VB, right? So this will cancel and it will go back to this. Understood?
Yes, sir.
So this is right, okay? So now if I write it this way, will it be okay? Plus VBC. I
Yes,
am
sir.
just changing this sign.
Yes, sir.
Fine. Now tell me, if VEC is increasing and VEB is constant, that means your VBC is increasing.
Yes, sir.
So if VBC, that means if in a diode, if this is VBC positive, if it is increasing, that means the reverse bias is increasing.
Yes, sir.
That means your depletion width will be more fatter.
Yes, sir.
Depletion width will increase, right?
Yes, yes, sir.
So if then that means your depletion width at collector base junction will increase. And what about the electrical length of the base?
Decreases.
This electrical width will decrease, this one.
Yes. Yes, sir.
So your WB will decrease. Fine.
Yes, sir.
So if your WB decreases, can you comment on what will happen to beta? If you have gone through the lectures, there is a relation 1 minus WB by 2 LB square of 1 minus WB by LB DE by DB NB by NE. Okay, this is your alpha. Okay, so from that, if you make certain approximation, what are the approximation? WB by LB is much less than 1, then you will find out that your beta will be inversely proportional to your WB. Okay, so if your WB is reducing, your beta will increase.
Yes, sir.
What if beta is increasing? IC is increasing.
Yes, sir.
That means we have started from here and we are reaching here. That means what? Your VCE increment will lead to increase in IC, and it is due to the variation in base width or modulation in base width. So this phenomena is called base width modulation. So what will it impact? Ideally, what should have been my profile? Ideally, this should saturate, right? And then be like this. Do you agree?
Yes, sir.
So if this should saturate, and then ideally this should be the profile. Ideal case. So in that case, what is your DIC over DVEC? If your current characteristic is like that, it is IC, it is VEC. So what is the slope? Slope is 0.
Yes, sir.
This by the way, this quantity is called G out. Okay, output conductance. Output conductance. Okay, and your DIC by DVBE is called your GM, or that is called transfer conductance or transconductance. So now this is the green case, ideal case. But what about this blue case or non-ideal case? Do you see that your IC DIC by DVEC is non-zero?
Yes, sir.
There is a line, right? If the slope is not zero, that means your output conductance is not zero. Now, if your base width modulation increases, that means base width modulation increases means DIC over DVCE increases, or in other way, if I change my VCE by a small amount, my VIC will now be much higher. So this will lead to your increment in G out. Okay. So the effect of base width modulation is the output conductance is increasing. Similarly, if somebody asks you that what will be the output this output resistance, so your R out is nothing but 1 over G out, it decreases. Okay, so base width modulation decreases output resistance. Can you tell me a side effect of this? Now I'm digressing a little bit, but I think you should know this. Why do we want my output resistance to be higher, or ideally infinity for an amplifier?
Uh, because device does not affect the current. Change in current. Change in current should be due to the input current. which input I provide.
Right, but in a more sophisticated way. That means my question is, why do I want R out or the out of an amplifier to be infinity? You see, these amplifiers are not, single amplifier is not sufficient. Let me put it in this way. So these amplifiers are generally cascaded, okay? Have you seen any cascaded amplifiers? Suppose one amplifier is giving you a gain of 50 and you want a gain of 2500. How will you get that? Or let's say you want a amplifier, you want a gain of, let's say, 1000. This is your V in, this is your V out. This is A1 amplifier, this is A2. Okay? You want your amplifier of high gain. What will you do? You will
Yes,
just put another amplifier of 20 in front of it. Okay?
yes, sir.
Fine?
Yes, sir.
Now, suppose this amplifier does not have a infinite output impedance, or I let me tell it in this way. If suppose it has an infinite output impedance, okay, so how will you get that? How will you write it? If R out is infinity, that means it is open circuit. Fine. And
Yes,
if
sir.
R out is not tending to infinity, or it is finite, then you draw the symbol as this, okay, and output impedance. Fine.
Yes, sir.
So suppose this is your A1, this is your some R out 1, and here you have another amplifier A2. What do you think will happen if this R out is not present? When R out is present in one case and R out is not present in another case. This is,
R out
let's
is,
say, case 1. In another case, it is like this. What do you think will happen?
if R out is there, then a path is there to loss.
A, a current will flow in this direction also, right?
Yes, sir.
That will reduce my gain, overall gain, or V out by V in will no longer be equal to A1 times A2. In this case, V out over V in is equal to A1 times A2. Okay. In this case, it is not, because a part of the current is flowing in this direction. This is non-ideal cascade connection. Okay. And this is your ideal cascade connection. You know about cascade connections?
Yes, sir.
So this is the way to more easily visual this. I can show you some more sophisticated way to go about this. You will see that in your MOSFETs, when you will see that there will be some capacitances also. Okay, this will slow down your circuits, by the way. So that's why you need to do much more analysis, and you need to do higher end stuff like two-stage stuff, and you need to compensate some using some Miller compensation and all. Those you will learn in later courses. But for the time being, you think it in this way. You take a RC circuit, okay, and take another RC circuit. This is R1 C1, let's say R2 C2, okay. So you take it as one block, you take it as another block, okay, and then you compute the transfer function V out by V in. Let's say this is H1, this transfer function is H2 between this to this. V out by V in S domain, then you will see that it is not, if you do properly with the KCL and KVL, you will see that it is not simply H1 of S times H2 of S. Okay, do you get it what I am asking?
Yes, sir.
So do this task at home. Okay, it will be very helpful for you, that you take two contraption. This is one RC circuit and this is another RC circuit. Compute H1 and then compute H2 and see if your H1 and H2 this condition is valid or not. If H1 H2 is giving you V1 V out S and V in, this will not be the case. Okay, so what is the way out? Generally people use a buffer inside. It's a unity gain amplifier with infinite output impedance. This is looking R out is infinite. Then if you compute your V in by V out, and this is your H1S and this is your H2S, in this case your V out over V in would be H1 times H2. Okay, you do this. Okay, it is very good. So this is the reason that this thing is not desired. Okay, I am biasing my amplifier at this region, in the forward active region, so I want it not to be having any output this conductance, or I want infinite output impedance or output resistance, so that my this circuit, this is by the way called loading. Okay, we don't want loading, so this is the solution. This is a buffer. Okay, do this at home, it will be a good thing to do. Okay, so now moving on to the next problem. Consider a uniformly doped silicon BJT have following specification. Okay, this is given, base doping is given, punch through is given. Okay, by the way, what is punch through? This is your PNP. So these are the depletion regions. This is your emitter, base, collector. Generally forward biased, generally reverse biased. So what is punch through, by the way?
When width is 0, tends to 0.
What width?
Base width, depletion width. When base
This,
is fully depleted.
which base width? We have discussed about two base width, right?
Electrical base width.
Electrical base width tends to 0, and why will that happen?
Because of biasing.
Which bias?
Reverse bias.
At which junction?
Base collector junction.
So if we keep increasing this voltage, so what will happen? This will try to enlarge, right?
Yes, sir.
So this will try to push, and there will be a situation when your this part, or this is your XDB and this part is XDC. So there will be a situation when your the voltage, this is, let's say, VBC, VBC, at which XB or your XDB is almost equal to your metallurgical base width. Okay, that is called your punch through. That means your collector is punching at the base. Okay, through depletion, by means of depletion. This is called punch through voltage. Fine. Now it is a PN junction. We can simply analyze it in form of PN junction. How? We wanted to find out the collector doping concentration. Okay. So now what do we have? This XD is the total depletion width at collector base junction. Okay. That is equal to your XD at base side plus XD at collector side. So what is that basically? From PN junction theory, we know that it is 2 epsilon S, the built-in potential phi Bi plus the reverse bias voltage VBC over Q times 1 over Na plus Nd, or in this case 1 over Nb plus 1 over Nc. Okay.
Yes, sir.
And also what do we know? We know from the PN junction theory that XdB times Nb is equal to XdC times Nc. Do you agree with that?
Yes, sir.
Why do you agree with that?
Sir, this is equation.
No, equation, but how does that equation come about?
When we
If
solve the
this,
electrostats.
it is nothing to do with the electrostatics, right? It is the depletion approximation. If you have suppose I am ignoring the emitter part, okay? There is somewhere here emitter. This is your collector, this is your base. This is a PN junction, right?
Yes, sir.
So there will be certain region depleted,
Yes, sir.
and there will be certain region depleted here also. So this concentration has to be same, right?
Yes, sir.
So this is what? This is your XDB, this is your XDC, and this is your NB, this is NC. So, and this is your you say rho. So your what happens? XDB times NB has to be equal to XDC times NC. So this is what we have written here. Okay.
Yes,
So your XD is equals to XDB times XDB plus XDC. If I take XDB common, I will have XDC over XDB. So your XDB will be equal to 1 plus, what is XDC by this? It will be NB over NC, right? XDC by XDB. If I take this side, so it will be NB over NC. Fine. So from this equation, we can write XD is equal to, or in other word, let me do it in other way. From this we can write XDB is equal to what? NC over NC plus NB times XD. So I have XDB equals to NC over NC plus NB times this entire thing, 2 epsilon S phi Bi plus VBC over Q times what we have, NC plus NB over NC times NB. Okay. So I have XDB is equals to square root 2 into epsilon s into phi bi plus VBC over Q. And here if I take NC inside, so it will have NC over NB, and this will be 1 over NC plus NB. So now what happens? Now we are told that this is the base width and at punch through voltage, so this XB will be WB dash when my 2 epsilon s phi bi plus 25, or the punch through voltage will be like that, 1 over NC plus NB. Okay, at this voltage XDB will be, or this will be entirely at this location, this depletion edge. So what will happen? And also it is given that VBI you can think that much less than 25 volt. Okay, so this thing WB dash is given as 0.5 micrometer. So 0.5 into 10 raised to minus 4, and if I do square, so I will be leaving with 2 into 11.7 into 8.854 into 10 raised to minus 14, and this I will write as 25 over 1.6 into 10 raised to minus 19 into your NC over, what is your NB? NB is given as 10 raised to 16. 1 by 10 raised to 16 plus NC. So everything is known, you need to compute NC. Okay. So if you compute your NC, it will come out to be 8.38 times 10 raised to 14 per centimeter cube. Okay. So this one will be your answer. Fine. You see in this problem also, you can note that this was your NB, this was your NC. Okay. So your NB is much more than NC. Fine. So the thing we have discussed, where did you discuss that? This was right. Okay.
Yes, sir.
So this is given. Now it is asked that what is the depletion width on the collector side. Again we know that XDB times NB is equal to NC times XDC. XDB we know 0.5 micrometer minus 10 raised to 4. NB we know 10 raised to 16. NC we know 8.38 and 10 raised to 14. From last problem we have computed, and we are to find out your XDC. Okay. So your XDC you can compute it at as to be how much? You can compute 0.5 times 10 raised to 12 divided by 8.38 divide 10 raised to 14. So it is 5.96 times 10 raised to minus 4 centimeter, or 5.96 micrometer. Okay. You see that your this entire stuff is how much? Your 0.5 micrometer, and the depletion itself only, it is not to scale, is your 5.9 micrometer. Okay. So you can imagine that your WC should be much more than WB. Okay. This is also one way to check. So here we can see that no answer is correct. So none of the above is the right answer to take. Okay. So for today, let us conclude with this problem only. So consider a uniformly doped NPN silicon transistor with following specifications. Okay. So let us draw the silicon transistor. So again, I will have this kind of depletion regions. This is my emitter, base, collector, and this is N, P, N. The doping is mentioned 10 raised to 17, 10 raised to 16, and 10 raised to 15. Okay. Determine the base emitter voltage. That means this one, VBE, such that the minority carrier concentration at NB at x equal to 0 is 10% of the majority hole concentration. Okay. So if we draw the carrier concentration, excess carrier concentration profile, so what will we have? We will have something like this and this. So this will not be that good. It will be like that. It will be like that. Okay. So it is asked that, and this is generally considered as your x equal to 0 point. Okay. So they want us to calculate what is the determine the VBE. So this is your delta N. This is P type. So minority carrier will be delta NB. So your delta NB is equal to, as it is P type. So what do we do, right? NP0 times e to the power VBE over VT. So at x equal to 0 is 10% of the majority carrier concentration. So what is the majority carrier concentration? This is the majority carrier concentration, right? And what is 10% of that? What is 10% of 10 raised to 16?
And 10 raised to 15.
10 raised to 15 is equal to, and what is your NP0? Is nothing but Ni square over 10 raised to 16 e to the power Vb over Vt. So 10 raised to 15 is equal to 2.25. Your Ni is equal to 1.5 into 10 raised to 10 at T equal to 300K. Remember that Ni is very high dependent function of temperature. Your Ni is what? NCNV exponential minus Eg over 2kT. Remember that? So it is very important whenever you are using Ni, mention the temperature at which you are computing Ni. So this will be 10 raised to 20 over 10 raised to 16 times exponential VBE over VT. So this will be your 10 raised to 33 or sorry 31 over 2.25 into 10 raised to 20 is equals to e to the power VBE over VT. That means your VBE would be 0.026 times logarithm of 10 raised to 11 over 2.25. Okay. Let us compute what that comes out to be. 25 logarithm of answer times 0.026. It will come out to be your 0.6374 volt. So this will be your right answer. Okay. So you remember what are the important diagrams in BJT. Okay. From device point of view, the important diagrams in BJT. First one is this. Second one is minority carrier concentration diagram. Third one is this current flow diagram. This carrier concentration diagram. So these are, and this is the current flow diagram. Okay. Output characteristics. This is called output characteristics. Okay. So this is how you go to about solving the BJT problems. So I could not start MOS capacitor today. So this MOS capacitor problems we will discuss in next lecture. Okay. So that's all for today. If you do not have any question, we can close the session.
Yes, sir. Thank you, sir.
Okay. Thank you.